Hello, this is video 52 and I'll be talking about two-dimensional collisions. So we just finished talking about elastic and inelastic collisions and we did them all in one dimension. So now we're going to combine that and make two dimensions. So this is very similar to when we talked about one-dimensional motion, horizontal and vertical, and then we put it together for projectile motion. We basically said that projectile motion was two one-dimensional problems stuck together. Well, same thing here. Two-dimensional collisions are just two one-dimensional problems stuck together. So here I just have a picture of a sample two-dimensional collision where the blue ball M1 is hitting the orange ball M2, but it's not hitting it right head-on. It's hitting it on the side here, so it causes both of them to go off at an angle. So now that means that this has become a two-dimensional collision because the final velocities have x and y components. So this is just one example. You could have a collision where you have one ball going to the right, one ball going up. That's a two-dimensional collision, as long as you have x and y directions for a few of the velocities. So the way that we're going to solve these types of problems is we're just going to solve two one-dimensional problems. So what you see here is the total momentum of the system in each direction is conserved. We have written conservation of momentum in the x direction. This is just like what we had before. We just have an extra subscript. We now have three subscripts. You see, v1 initial x, v2 initial x. If somebody can make a song with this, you will get a point extra credit on the test, because I just think it's fun to say m1 v1 initial x plus m2 v2 initial x. Anyway, I don't want to get carried away, but let me know if you make a song with this. So then we have equals m1 v1 final x plus m2 v2 final x. So it's just the same equation, we just have this extra subscript, and then we have the equation again for the y direction. So there's really nothing new here, just that we have an extra subscript, but we're going to solve two-dimensional problems just like we did one-dimensional problems. So I actually wrote out the steps here. So here we're now going to define up to 8 velocities. Before we were defining v1 initial, v2 initial, v1 final, and v2 final. I was always writing those down. Well, now, because we have some velocities in the x and some in the y, then we just are going to write a extra subscript here, x, and then we're going to rewrite them again, v1 initial, v2 initial, v1 final, v2 final, and add the subscript y. So that's what I mean by define up to 8 velocities. Now, some of them will be 0, sometimes you'll stick together, so that will reduce your velocities as well. And then after you define the velocities, you write down your equations, cross out the terms equal to 0, and solve for the unknown velocity in each direction and combine if needed. So what I mean there, let's say that you end up solving for v2 fx and v2 fy, then you can combine those two with the Pythagorean theorem to find v2 f. So let's do one example of a two-dimensional collision. So this one has a car going east 25 meters per second and another car going north. The I and the J, we don't use that notation in this class, that's just a picture. It just shows you the x and the y directions. So let's go ahead and write down our givens. So M1 is going to be that first car with 1,000 kilograms, and M2 is going to be the other car with 2,000 kilograms. So then we write down our givens. So we have V1 initial x, V2 initial x. Now usually we have V1 final x and V2 final x, but they're sticking together. So we just have V final x. We don't need to put V1 final x and V2 final x because they're the same. They're sticking together. And then we also write down V1 initial y, V2 initial y, and V final y. To this day, when I do collisions, I always write down the givens because I cannot keep up with all the variables. So let's figure out, because see, we only have two numbers. And a common mistake with these problems is that people just put all these numbers into one equation, and that is not allowed. So the first car was going east, that was horizontal, that was the x direction. So that was v1 initial x, that was 25 meters per second. So since it was only going horizontal, the first car, the blue car here, was not going north or south. v1 initial y was 0. And then the 20 is the initial velocity of the other car, which is north, which is in the y direction. So the 20 is v2 initial y. And that means that the second car does not have any initial velocity in the x direction. And we're looking for the final velocities. So really the hardest part for collisions is just making sure that you identify your givens correctly. And then we're just going to plug and chug into our two equations. So we have m1v1 initial x plus m2v2 initial x. And I'm still waiting for someone to tell me if they've made up a nice song. And so we have m1v1, sorry, they stick together. I got distracted talking about the song here. So the little things, right? And then v final x. So, and then we're going to write the same thing in the y direction. m1v1 initial y plus m2v2 initial y equals m1 plus m2 times v final in the y direction. So cross out what's equal to 0. v2 initial x is 0, so this whole term is 0. And we're trying to solve for vfx. So vfx equals m1v1 initial x over m1 plus m2. Plug in the numbers, and we have 1,000 times 25 over 1,000 plus 2,000, and that's going to give us 8.33 meters per second. Then do the same thing in the y direction. We have v1 initial y was 0, so that first term was 0. So v final y equals m2 v2 initial y over m1 plus m2. Plug in those numbers. I'll let you plug them in. It's just going to be 2,000 times 20 over 1,000 plus 2,000, and that's going to be 13.3 meters per second. So, if you remember our talk about vectors, that means after the collision, the two cars have an x component going to the east because it was positive. They have a y component going north because it was positive. And that means that they're going diagonal this way, which we already know from the picture. And so we're trying to find VF, so we're going to use the Pythagorean theorem because we have a right triangle. So VF equals the square root of VFX squared plus VFY squared. So plug in square root of 8.33 squared plus 13.33 squared, and we'll get 15.7 meters per second. That's our final velocity, but we're not quite done. Velocity has a direction. Don't forget, we need to specify what is this angle theta here. It has an opposite of the y as the y component, the adjacent as the x, so we can use inverse tan of the y over the x, VFY over VFX, and that's going to give us 58.0 degrees. So that is the velocity, the magnitude, and the direction. So just one more thing, as I recap, I do have a very important note to make, just because I've seen so many mistakes with this, is pay attention to the sign of your velocities. Unfortunately, in this example, two initial velocities were positive, so I didn't even have to mention it. But if the car had been going to the west instead, right, then that initial 25 meters per second would have been negative 25. If this car had been going south, that would have been negative 20. If one of these cars had been going at an angle, right, this way, then it would have a positive x component but a negative y component. So you really have to pay attention to those negatives, otherwise you're going to get a completely different answer. So two-dimensional collisions, just write down conservation of momentum separately. Do not put the x variables in the same equation as the y variables. Keep them separate until you're ready to combine them at the very end when you have found the x and y components.